We're going to be looking at and probabilities. There are two types of and probabilities that we're going to be looking at. One is independent, and that is where the outcome of one event does not affect the probability of the other event. And the second type is dependent, where the outcome of one does affect the probability of the other event. And we have our formulas over here, which seem a little bit more complicated than they actually are. Now, we've already done some of these problems with the last handout that we did with looking at the probability of drawing marbles. So this is the same type of thing, except for now we're looking at standard deck of playing cards. And my directions say determine the probability of each of the following with replacement and without replacement, and write your answer as a fraction. So what this means with replacement, you're going to draw a card, put it back in the deck, draw a second card. And without replacement means you're going to draw a first card, keep it, and then draw a second card. All right, so with replacement, drawing a 4 and then drawing a king, the probability of drawing a 4 is 4 out of 52. Now I'm going to replace that card, and then I'm going to still have 52 cards to choose from, and the probability of getting a king is 4 out of 52. So to find this compound probability, I'm just going to multiply those two fractions together, and I get 1 over 169. Now, without replacement, I start the problem off the same way. Probability of getting a 4 is 4 out of 52. Now, I don't replace the card. I have to assume that I got that 4 on that first draw. Now there's only 51 cards left, but I still have all 4 kings. So the probability of getting a king is 4 out of 51, and that will multiply to give me 4 over 663. Here I have the probability of getting 2 reds. The probability of getting a red is 26 out of 52. I'm going to put that card back into the deck and fresh start. So now my second draw, I still have the probability of getting a red is 26 out of 52. Now you could also think of this probability of getting red is 1/2, because half the cards are red, and 1/2 times 1/2 is 1/4. Now, if I don't replace the cards, I'm going to have 52 cards to draw from the first time. This is kind of like how I like to do the problem. I sort of do things backwards, not backwards, but in a different order. I have 52 cards to choose from the first time. I have 51 cards to choose from the second time. So once I get those fractions, those denominators written down for those fractions, then I can really concentrate on my numerators up here. The probability of getting a red card is 26 out of 52. Now I have to pretend I got a red, so now there's only 25 reds. And when I multiply those together, I get 25 out of 102. Okay. So that's basically all there is to it with these problems. So what you should do here is pause the video and complete this table, and then come back and check your answers. Okay, there are your answers, so check those and be sure you've got those right. And we are going to go on to this next section here. The directions say to identify each of the following as dependent or independent, and write the probabilities as a decimal. Problem 1, randomly selecting a 4-person committee consisting entirely of men from a pool of 10 men and 8 women. Now, this problem may seem a little odd because we have men and women here that we're choosing from, but if this were a bag of marbles with different colors or different colored blocks, I don't think there would be a problem. This is no different than those problems. First of all, let's figure out if we have a dependent or an independent event. And when I draw a person's name, I'm not going to put the person's name back in the hat. So what's going to happen is that every time I draw, there's less people to choose from. So the probability is going to change from one time I draw to the next. So I have dependent events. So what happens on that first draw is going to affect the second draw. Now I'm going to draw this here. It's kind of like a bag, like we would have a bag of marbles, but in here I've got 10 men and 8 women that I'm going to be choosing from. So I have 18 people altogether that I'm choosing from. Now I'm going to select a person's name out of the hat, and I want that person's name to be a man's name. So probability of getting a man's name is 10 out of 18, 10 men. Now I don't replace that name, so now I only have 17 names to choose from. Now to pretend I got a man's name on that first try, so now I only have 9 men's name, and then we just keep going like this. 8 out of 16, 7 out of 15, and we've got our 4 people there that we've chosen, and when I multiply that together, 0.0686. Problem 2, rolling 2 5s on 5 roll of a die. When I roll that first die, the first time I roll the die, it's not going to have any effect on what happens on my next roll. So I have independent events. I'm going to go ahead and just abbreviate that. The probability of getting a 2 is 1 out of 6. When I roll the second time, the probability is 1 out of 6. And the third time, and the fourth time, and the fifth time. Okay. So I'm going to write this as 1/6 to the 5th power. When I put that in my calculator, it's going to be a little bit easier to put that in as an exponent instead of having to write all those fractions in my calculator. And I'm going to round this to 6 decimal places, so 0.000129 is my answer. Now the next couple of problems here are just like what we've been doing. Problem 3, we're writing our answer as a decimal, and the problems down here on this second section, we're writing our answer as a fraction. So again, pause the video and work on problems, this problem 3 here, and then problem 1 through 3 down in this section, and then come back and check your answers. Okay, there are your answers for those few problems. So check that, be sure that you have that right, and then we'll scroll on down to the last 3 here. Okay, problem number 5, the probability that the next 5 babies born are all girls. Well, it doesn't matter whether you have 1 child or 17. The chances that it's going to be a girl is always 1/2. So these are independent events. Probability of getting a girl for your first child is 1/2. The probability that your second child is a girl is 1/2, and the third, and the fourth, and the fifth. And I can write that as 1/2 to the 5th power, and we are writing this answer as fraction, so that's 1/32. Every time you have a child, the probability that it's a girl is 1/2. Problem 6, rolling a 2, a 5, or a 1 on 3 rolls of a fair die. What you roll on that first time you roll a die is not going to affect the second and the third roll. So these are independent events as well. Probability of rolling a 2 is 1 out of 6. Probability of rolling a 5 is 1 out of 6. And the probability of rolling a 1 is 1 out of 6. So that multiplies to give you 1 over 216. And then the last problem, the probability of drawing 3 aces in a row when the card drawn is not returned to the deck each time. So since they're not returned to the deck, that's without replacement, another way to say that, is going to end up being dependent events. What happens that first time is going to affect the second time. Or, well, you could say it, what happens on that probability of that second draw depends on what the first draw was. Okay, I want 3 aces in a row. Probability of getting an ace is 4 out of 52. Now I have to pretend I got an ace, so then the probability is 3 out of 51. And put that back, or we're not putting it back, and then I end up having only 50 cards by the time I make my third draw. And I have to pretend that I keep getting that ace, so now there's only 2 aces left. Now, if I put all 3 of those fractions in the calculator and tried to write this as a fraction, it's not going to work because my calculator will only display so many digits in my denominator. So what I'm going to have to do is to put 4 over 52 in the calculator and simplify that, and that is 1/13. 3 over 51 is 1/17, and 2 over 50 is 1 over 25. So now that I have all 3 of these fractions simplified, I can multiply these fractions like I learned in elementary school. Just multiply the numerator straight across, I get 1. Multiply the denominators straight across, and you can use your calculator for that, and you get 5,525.